things, different languages call the same thing by different names, but in chemistry and in the sciences in general, we try to make things the same no matter what country you're from and what language you speak. And so we're going to learn how all these crazy, strange names that you see on packages, on the stuff, cleaning sprays underneath your sink, or food packages in your pantry, where some of those names come from. And we're starting with ionic compounds. We've spent a lot of time already talking about metals and nonmetals and cations and anions. I'm going to do it a little bit more and remind you that most of this, all of the stuff that I'm talking about pertains to the group A elements. And this beginning part is with the metals. Okay? And at the end, we'll talk about the nonmetals. The group A are the representative elements. They're the elements in the S and the P block on the periodic table. So those first two columns and the last 6 columns, we'll get to the transition metals towards the end. Monatomic mean, I'm going to escape because I don't know this. I wonder if I saved it. Uh-oh. Oh my gosh, it's one of those days, you know? Discard, discard, discard. Oh, heavens to Murgatroyd. I don't know why that's on there. Oh my goodness, gravy. This start to finish, today's been just wonderful. And now my laptop is frozen again. Bad words. That's what I want to say is bad words. It's not doing anything. Wow. Oh, I guess this is a sign that I need a new laptop. And I can't even get to you guys in Chrome, which means, oh my gosh, I'm gonna cry. It's gonna take a solid 10 minutes for me to shut down my computer and come back. I'm going to ask you to go to the diagram in your classwork feed, because I can't even get to, oh, hey, maybe I can, hang on. Woohoo. All right, let me shut something down here. Gosh, I was about to start crying. Try and close this. Don't save. To reopen it. I wonder if it's my little pen pad is messing with my computer. Try again. Thank you, Mr. Wolken. I am trying to keep my poop in a group here. Okay, yeah, my inside is screaming. It's like a duck on the water, right? I don't have that one. Looking calm on the surface, not calm inside. Spinning beach ball of death. Thank you, sorry. I'm trying. Okay, it's opening. Yes. Yay, and none of the silly annotations on there. Woohoo! All right. I'm gonna try my little X pen thing so I can notate as we go. Hopefully it doesn't freak it out again. Wow. All right, here we go. Thank you guys for your support. Okay. Naming things. Group A. Those are our representative S&P blocks, the valence electron guys, right? Whether they're metals or non-metals. Turns out you can figure out their charge super easy by just looking where they are on the periodic table. Remember, monatomic means one. Mono means one, I should say. So this should be one atom. Turns out there's always an exception just about to nearly everything I'm going to say ever in chemistry. And mercury is considered a monatomic ion, even though the mercury 1 ion actually has 2 mercury atoms. It's so irritating. But normally, and we're not going to pay attention to mercury, okay? Normally, the metals and the non-metals are either going to have positive or negative charges respectively because they either gained or lost or gained electrons. And it's the valence electrons that matter. Except if you're a transition metal. There's so many exceptions, but just hang in there, Okay, group 1, group 2, group 3. In the old days, we used Roman numerals. The A group elements were the representative elements. Now, of course, that's group 1, that's group 2, and this is group 13. But they're all going to lose electrons. When you lose a negative, you become positive. Okay? You have more protons than electrons. And those make cations with positive charges. Super cool naming cations. You just name the metal. You can write, you should say ion after it. You don't need to say cation. Right? That's extra letters. That's an extra syllable. If you're talking about metals, of course they're going to be cations because they lose electrons. So when we name them, we just name whatever the element is, blank ion, sodium ion, calcium ion, whatever it is. Very, very easy. Okay, and again, group 1, everybody ends with S1. Everybody in group 2 ends with S2. Remember, there's no p electrons, p orbital electrons at the outermost. Okay, they can have p electrons underneath, but the valence electrons are the outer electron shell, and they don't have any of those. Okay, now aluminum's weird, right? Beryllium's up above it. This is group 13. This is really the only element in group 13 we have to worry about. Okay, and it ends with S2P1 because it has 3 valence electrons, 2 and 1. So it's going to end up with a +3 charge. It's going to lose all 3, and we just call it the aluminum ion. You don't need to say aluminum cation, because if you're talking chemistry, you should know that aluminum is a metal and loses its positive as ion. Every element in group 1 has a +1 charge. Again, the 1 is not necessary. It's a waste of pencil lead. If you want to write it, I have no problem with it being there. But all of them lose their 1 valence electron when they react. Their outer layer gets stripped off by another element. Everybody in group 2 forms +2 ion. Again, the proper way to write these is with the magnitude first and then the sign second. I don't care if you do +2, and you will see I go back and forth. It doesn't matter to me. So they all lose both of their s orbital electrons in their outer shell. Just a little throwback to when we were talking about nuclear chemistry. Remember, we talked about the radium girls, these poor women that were working in the factories and painting dials with radium paint, that whole horrible scene. Turns out the reason why their bones and their jaws in particular crumpled and their teeth fell out and everything else is because radium and calcium are in the same family. They both have 2 valence electrons. Radium can bond to the same things that calcium would bond to. I'm not going to go into it right now because it's too much information, but just know that obviously you guys know your bones are made and your teeth are made of have calcium in them. It's compounds. It's not pure shiny silver metal calcium, but the radium can substitute into those matrix, and it's constantly evolving. You know, your bones in your teeth aren't static. I don't know if you guys know that. Those of you that have parents that are doctors might know that. There's a couple of you in this period. But your bones are constantly evolving. They're constantly changing. You're constantly losing some and building some. And so the radium can get incorporated into the bone structure. And then, of course, when it undergoes nuclear decay, it's no longer going to have the same valence electron structure. It can't stay bound to the same stuff, and the bones break really easily. It's crazy. Horrible, horrible, horrible. Anyway, so sorry, I really got sidetracked in this class on that. Sorry about that. Anions, okay, non-metals form negative ions, okay, and that's because they gain electrons. Those extra electrons are to get them to noble gas configuration. Everybody wants their octet, and so they're going to add electrons, getting them from a different atom, from a metal. The book has this little trick for figuring out the charge. It's really not that hard to just look at a periodic table, but if this helps you, great. They say subtract 8 from the group A number. Here's the problem. We don't use this all the time, and I'll show you an example. So oxygen, where's oxygen? Oxygen's here. It's in 16 on the modern periodic table, but back in the old days, that was group 6A, which now we use Arabic numerals sometimes to group 6A. So if you take 6 minus 8, you get the -2. If it helps you, great. It bothers me because we're not subtracting electrons. Okay, we're adding electrons, but I don't know. Maybe it'll help you. Okay, chlorine is in group 17, which used to be 7A. And so 7 minus 8, of course, is -1. And again, we don't write the 1, but you can if you want to. And then phosphorus is in group 15, which is 5A. 5 minus 8 is -3. So that tells you how to get the charge. Honestly, it's really just as easy to number, and I'll go over that with you in a minute. But if it helps you, great. All right, the next trick, again, and I've already mentioned this, is how we name them. So anions, we modify the name of the element. We do that by changing the suffix. We change the ending, and we keep the front part. Sometimes it's only one syllable, sometimes it's a couple. It depends on the element. Again, there's not a rhyme or reason that I have ever noticed for this. You'll just have to become familiar with how it sounds. Okay, so oxygen, some of you can probably figure out what this is going to be. But oxygen, we could say the oxygen anion, but it's easier to say oxide. Okay, when you see the IDE ending, you're supposed to know it's the anion. Chlorine, I already talked about this, I think, on Tuesday. Chlorine ion, chlorine anion is chloride. Okay, right? We don't say sodium chlorine, we say sodium chloride. Phosphorus, probably see where this is going. No, it becomes phosphide. So oxygen, we drop 2 syllables. Chlorine, we just dropped the last one. Phosphorus, we drop 2 as well. Why is it 2 for some and 1 for, I don't know. It just is. Okay. So hopefully that's not too hard. Again, nitrogen's family is group 15, oxygen 16, 17. Of course, we're not talking about noble gases because they don't form ions. They all have 5 valence electrons, 6 valence electrons, 7 valence electrons, 3 more electrons, and you get the noble gas configuration. 2 more electrons, you get your octet. 1 more electron, you get your octet. Everybody in nitrogen's family forms a 3 minus. Everybody in oxygen's family is 2 minus. All the halogens are -1. And so their names are easy, right? Phosphide, nitrogen becomes nitrite, arsenic becomes arsenide, oxygen is oxide, sulfide, selenide, chlorine becomes chloride, fluorine becomes fluoride, bromine becomes bromide, iodine becomes iodide. Hopefully that's not too bad. So again, this is the table, and this looks a lot like our dot diagram setup in our organizer that you're going to work on. Here's my trick. Whatever. It's super simple. You're just numbering 1 through 8, right? You're ignoring the 10 transition metals in the middle. But 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Okay. Everybody that's a metal is going to lose electrons and form a cation. You have 1, you lose 1. If you have 2, you lose 2. If you have 3, you lose 3. Okay, so you end up with +1, +2, +3. Carbon's family does some weird stuff. We're going to talk about that in a minute, or actually I won't get to all of it until tomorrow. So we just kind of ignore, a lot of books show you this +-4 thing for carbon. That's really kind of weird. 3 more valence electrons, right? You have 5, you need 3 more. You put in 3 negative electrons, 2 negative electrons, 6 plus 2 more, 1 electron, right? It goes pretty simple. 1, 2, 3, skip over this one, 3, 2, 1. And of course, noble gases don't need any more valence electrons because they're already full. So for me, it makes more sense. Keep in mind, electrons are negative. Lost 1, lost 2, lost 3. Mixed up group. Gain 3, gain 2, gain 1. All right, now, I really would like, if anybody have any questions, I'm scared to change my screen. So if anybody has any questions right now, please ask them. Okay, I'm gonna keep on keeping on and hope nothing goes wrong. All right, transition metals. Those are not the S, not the P, but the D block elements in the middle. These are the elements that you think of as real metals. In particular, the 2 that you absolutely have to understand about are copper and iron for this level of chemistry. Chromium is important, manganese is important, cobalt is important, mercury is a pain in the patooties. We'll talk about it later. Silver, gold are in the same family with copper, zinc's next door. You know, there's a lot of real metals in the transition metals, right? But also, you know that the D block, remember the S has 1, the D's, there's 5 D orbitals, and the P's, there's 3 of them. So remember when you're on this period, 4th period, it's the 4S, the 3D, and then the 4P. Remember that the S fills before 4S fills before the 3D. Okay, so turns out weird stuff goes on. Remember, electrons aren't stationary. You're going to put little dots on your organizer today, but electrons move around. Okay, and even if they're in that orbital, they're only there 90% of the time. That's the probability thing we talked about ages ago. So they're bouncing around at the speed of light inside of atoms. Turns out they can do some little weird movements back and forth between the 4S and the 3D, or between the 5S and the 4D. And so they end up with more than one charge. Depends on what else they're bonded to, but they can form ions of different charges. And the 2 most important elements that you have to learn are copper and iron. We've talked about this before. This is actually from chapter 5. Okay, So I'm bringing this back again. I've had it in a couple of slideshows and I haven't talked about it, but this is the time. So copper is element 29. Okay, you know that up to here, right, noble gas configuration, it has 2 in the 4s and 3D has 9. So S is full. 1, 2, 3, 4, 5. Seats on the bus rule, Hund's rule, 6, 7, 8, 9. This last d orbital is only half filled, and that makes it a little out of balance. Remember, the cramming 10 electrons, 10 negative things in the same region around the nucleus is going to take more energy than just putting 2 in. And so we're going to see some weird stuff. Okay, copper, it turns out, forms a +1 ion and a +2 ion. It loses 1 electron with some. In some compounds, it loses 2 in others. Why is that? Well, the s orbital electron can move. Okay, it's not that big of a shift for it to slide into a d orbital. That's the easiest way to explain it. So if that 1 electron that's in the 4s goes bye-bye, it would form a +1 ion. If those electrons don't move around, if they just stay in the s, it'll form a +2 ion. So again, the electrons in the s's and the p's are the valence ones. Those are the ones that are supposed to be gained and lost. But once we get into bigger atoms, they mix things up a little bit, right? And it's confusing, and I know that, and I just want you to understand that it happens, and hopefully this will help remind you how this happens. So again, 4s fills, then the 3b would fill. So that's the proper way to do the electron filling diagram for copper. However, again, if one of those s orbital electrons moves into a d, the d orbital, 5 orbitals get balanced and symmetrical and steady, I don't know, lower energy. And so we just have 1 in the s. Okay, so we lose that 1 in the s. This is what the electron configuration would be. And if we lose 2, both of the s's, configuration, yeah, this is still out of balance. It happens. Okay, and again, there's no, I don't have a way to tell you how to know when it's going to happen. There isn't a predictability. It just comes from working with the compounds to know which one it's going to be. Okay, so don't freak about that. Another interesting thing about transition metals is that they're very colorful when they're in solution. I should say their ions are colorful. So ionic compounds, you'll end up with a positive and a negative bit that comes apart sometimes in water. And sometimes they have colors. And those colorful ions, those colorful compounds can be used to make paint pigments and ink pigments. So that's kind of neat too. There's also several of them that are really dangerous. But yeah, and I think I'm gonna, okay. Oh, I moved that slide around. Okay, never mind. Sorry, talking to myself. I got 10 minutes. I'm gonna do this. All right, like other metals, the charges have to be determined by the electrons lost. Okay, cations lose electrons. So the question is, when is it going to be a +1? When is it going to be a +2? For right now, you just need to know that we have to indicate which one it is when we name it. We have to be able to distinguish a copper compound, copper sulfate. You have to know which form of copper ion you have. And I'll show you how to figure that out, but for right now, it's just roll with me on this one, okay? Iron does the same thing, but iron forms a +2 or a +3 ion. And these are the 2 that you have to know. Mercury is a +1 and a +2 like copper, but it does weird things. Lead and tin are +2 and +4. It's weird. And so there's two ways to name transition metal ions, okay? And this is just for transition metals. The representative elements, I don't think I emphasized that at all in the earlier classes. This is only for those transition metals. It's not for elements that are representative. Okay? There's something called the stock system, and there's something called the classical method. Your friend is going to be the stock system. It's super easy. Okay? In the stock system, you use a Roman numeral in parentheses after the name of the element to tell you the charge. So iron, it turns out, can make a compound with oxygen like this and like this. Okay? And oxygen is in both of them. Iron is in both of them, but they're in different proportions. Here it's 1 to 1. Here it's 2 to 3. They actually have different colors, and they actually have very different other properties as well. Okay, Fe2O3 is rust. FeO is a black compound. Okay, so you know the color of rust, it's rust colored, but they're both made of the same two elements, but they look very different, and that's because they have different iron ions. And so when we name them, we will name them with the Roman numerals. This one is iron 2. I'll tell you how to figure that out another day. And this one is iron 3. Right, so we have to have a way to signify that, because I can't just say iron oxide. Okay, I have to throw in the Roman numeral so I know which one of these compounds I'm actually talking about. I forgot to mention that in the other class. Oh well. So iron 2 loses 2 electrons. Iron 3 loses 3 electrons. They have different characteristics, so they deserve different names. All right. The icky one is the old style, the classical style. So classical, you know, ancient times, the Greeks, you know, we used to use Latin all the time. So ferrum is the original name of iron. That's why it has this weird Fe for its symbol. Iron with a +2 charge used to be called ferrous. And iron with a +3 charge is called ferric. So we changed the ending, the suffix, to indicate the charge. The problem is OUS just means the fewest electrons lost. And ic means the most electrons lost. Because the transition metals lose different numbers of electrons, this name is not that convenient for, especially for beginning chemists, because ferrous means -2 electrons, but cuprous only lost 1 electron, as I'll show you in a second. Just know Roman numerals make life way easy. You don't have to guess what the charge is. You just look at the numerals. So again, copper is cuprum. It can be +1, it's called cuprous, and +2 is cupric. So for iron, that was the 2 charge and the 3 charge. So these endings are great if you know more about chemistry, but they don't tell you the actual value. Okay, it's much better if you just say copper 1 and copper 2. You don't have to guess what the charge is. All right, I'm going to stop right there. See if there's any questions. Hopefully this doesn't crash and burn on me. All right, questions right now? No? Okay. Jack's all good. Here we got going on messages. All right, I'm going to switch you now to the dot notation organizer, which some of you probably have already opened up. This is in your classwork feed. These little blue boxes are text boxes to type in. It's pretty much just some vocabulary up here. It's all old stuff at this point. Valence electrons, those are electrons in the highest energy level. Just a reminder, those valence electrons are the ones that bump into other atoms. So those are the ones that can bond to other atoms. So that's what goes here. These are the electrons available for bonding. Octet, you know, that's 8 valence electrons. You know, noble gas configuration means the valence electrons equal that of a noble gas. Duh. Okay, usually that's 8. Usually that's an octet. But sometimes for little tiny elements, helium is as good as you get. So 1s2 is the configuration of helium. These next 3 lines you should be able to do. So what are you going to do for me for homework? You're going to use these little dots and move them around. So group 1, group 2, group 13, remember the transition metals are in the middle, 14, 15, 16, 17, 18. Group 2 has 2 valence electrons. Group 13 or 3A has 3. Group 14 or 4A has 4. Right? Everybody can count to 8, right? You're going to take the symbol for the element that's at the top, put it in the box, and then you're going to move dots. And the dots, you can select more than one, right? Hold the shift key down, and you can select more than one and move them. And you can bring them to the front if you need to. And remember, for group 2, they should be as far apart as possible from each other, right? Electrons are going to repel each other. Okay. Group 13 or 3A has 3 dots. You got the idea. Everybody that's a cation is going to lose. Oh, and then type this in for group 14. They share their electrons. The first 3 elements in group 14 share electrons. They don't lose or gain, and they form what are called covalent bonds, which we'll get to in a bit. All right, phosphorus has 5. It's going to gain 3 more to get an octet. Oxygen's family sulfur gains 2 more to get an octet because they have 6. Halogens have 7. They gained 1 more. And then, of course, the noble gases have 8. Okay, they don't gain, lose, or share because they're already happy atoms. They have their octet. So that's due tomorrow before class. Any questions on the graphic organizer? All right. All right. Have a wonderful rest of your day. Stay safe. Drive safely if you're out on the wet roads. I'll see you tomorrow. I'll stick around if there's any questions.